Hello, in our video we'll be talking about the forces and motion that occur when shooting a basketball.
Gerald Wallace will inbound. He's got Jeff Green, Kelly Olynyk, Avery Bradley, and the dangerous Jordan Crawford. He tried to hang on and win. This is Green for the win. He did it! Jeff Green wins the game for Boston on a corner three. Oh my.
In this situation, we assign the horizontal displacement as 6.7056 meters, the distance from an average NBA net to the corner three. Jeff Green completed his shot in 1.2 seconds, which is the time we will use in this situation. We don't know how Jeff Green's angle of release was, nor his height of release, but we can assume it is at 10 meters and 55 degrees, the average height and release of an NBA player.
There are no other forces acting upon the ball in the horizontal, so the initial velocity is equal to the final velocity. This means we can use the average velocity equation to find both the initial and final velocity. This value is 5.585 meters per second. Because the velocity does not change, the acceleration on the horizontal is 0 meters per second square.
To solve this problem, we will have to split the parabola created by the shot into two halves. We will have to divide both our time and displacement by 2. Our time is now 0.6 seconds, and our displacement is 3.3528 meters. At the top of the parabola, the final velocity in the vertical is 0 meters per second. We know that the horizontal velocity is 5.88 meters per second, and the angle of release is 55 degrees, allowing us to solve for the initial velocity using SOHCAHTOA. The number we get is 7.9805 meters per second. We now have solved for every value except the vertical displacement and vertical acceleration. We can use the big 5 to solve for these last two values, since we have 3 out of the 5 variables solved for. Using the big 5, we figured out that the vertical displacement is 2.39415 meters, and the vertical acceleration is 13.3 meters per second squared.
We have figured out all the properties of motion for Jeff Green's clutch jump shot for the second half of the parabola. Final velocity and initial velocity in the vertical would switch values, and acceleration would be positive instead of negative. The rest would remain the same. By using Newton's second law, force net equal to mass times acceleration, with us already knowing the mass of the ball being 0.62 kilograms and an acceleration of 13.3 meters per second squared, we get a force net of 8.25 newtons. In the clip of Jeff Green shooting the basketball, we can see the applied force when holding the ball and going up to shoot, with the force of gravity against it. When Jeff Green goes for the shot and lets go, the only force that is affecting the ball now is gravity from the earth pulling the ball down. As you can see in the force diagram and interaction diagram, when Jeff Green is holding the ball and going up to shoot, there is a force of gravity and its own applied force. The applied force is greater, meaning there's acceleration. And when Jeff Green lets go, the only force that is being now applied to the ball is gravity. Using Newton's third law, for every action there's an equal and opposite reaction. It can be said that when Jeff Green puts force onto the ball for it to accelerate towards the net, the ball has the same amount of force, with the same forces both starting and stopping at the same time. But the ball is causing Jeff Green to accelerate in the opposite direction, so further away from the net.